Hello and welcome. Today, we are diving into a whole new dimension of numbers. We're going to leave that familiar, cozy number line behind and step into the absolutely fascinating two-dimensional world of the complex plane. Think about it. We all know the number line, right? Any real number you can imagine has its own little spot on it. It's a single, straight dimension. But what about a number like, say, 3 plus 4i? Where on earth does that I part go? It definitely doesn't fit on our old number line. So, what's the solution?
Well, here's the brilliant answer. We just add another dimension. It turns out complex numbers can't be ordered on a line like real numbers can. They need a plane, a flat, two-dimensional surface where one axis, the horizontal one, handles the real part, and the other, the vertical one, handles the imaginary part.
So here's our game plan for today. We'll start by officially moving beyond the number line and then learn how to actually map these complex numbers visually. From there, we'll get into some really cool new ways to describe them using distance and direction, which, believe me, leads to a super powerful new identity. And finally, we'll put it all to the test with some real solid examples.
All right, let's start right there. Moving beyond the number line. We've figured out that complex numbers just need more space than a single line can give them. You know, this jump, this conceptual leap from one dimension to two, is really the key to unlocking everything that's cool about them.
So how do we visualize this new space? How do we map it out? Well, for that, we turn to a fantastic tool called the Argand diagram, named after the mathematician Jean-Robert Argand. Just think of it as our GPS for the complex world.
An Argand diagram is basically your standard coordinate grid, but it's been given a brand new job. The horizontal x-axis, that's now the real axis, and the vertical y-axis, that's our imaginary axis. This means every single complex number, every x plus iy, has its own unique address, its own specific point on this plane. And you know what? Plotting these numbers is incredibly simple. To plot 2 plus 3i, you just go 2 units along the real axis and then 3 units up the imaginary axis. Boom, right there at the point 2, 3. For 5 minus 3i, it's 5 units across the real and 3 units down. See? It's just that intuitive.
Okay, now that we can actually place a number on the plane, we can ask much more interesting questions. Instead of just its coordinates, what about, say, its distance from the center? And what's the direction to get there? This brings us to two absolutely crucial concepts, the modulus and the argument.
Let's break this down. The modulus, that's just a fancy word for the straight line distance from the origin, the center of our map, out to our point. If you picture a right triangle, the modulus is just the hypotenuse. Simple. And the argument, that's the angle that this line makes with the positive real axis. So, remember, modulus is distance, argument is direction. This picture just makes it all click, doesn't it? Look how our complex number forms a perfect right-angled triangle. The real part, x, is the bottom side, the imaginary part, y, is the vertical side, and our modulus, which we call r, is the hypotenuse. The argument, theta, is just the angle at the corner. We're right back in familiar trigonometry territory here.
So why are we going to all this trouble? Because defining a number by its distance and its direction, its modulus and argument, gives us this incredibly elegant and powerful new way to write it. This is what's known as the Modulus-argument form.
So how do we get this new form? It's actually a really slick substitution. We start with our standard z equals x plus iy. Now remember that triangle? Well, from basic trig, we know that x is just the modulus, r, times the cosine of the angle, and y is just r times the sine of the angle. So we pop those back into the original formula, factor out that r, and we're left with this beautiful new expression. And there it is, z equals r, the modulus, multiplied by the quantity, cos of theta, plus I times sine of theta. All the information about that number, its distance and its direction, is captured right there in one tidy package.
Okay, so we've got this powerful new tool in our toolbox. But theory is one thing. Let's get our hands dirty and see how it actually works in practice. We're going to run through some examples to really make sure these concepts stick.
All right, first up, let's find the modulus and argument for the complex number z equals minus 3 plus 4i. That negative real part is what's going to make this one interesting. Now listen up, because this is probably the most important tip I can give you. Always, always sketch a quick diagram first. The number minus 3 plus 4i is in the second quadrant, right? Knowing which quadrant it's in is absolutely vital when we calculate the argument. Forgetting to check is, without a doubt,
The number one mistake people make.
The modulus part is pretty straightforward. Square root of -3 squared plus 4 squared, which gives us a nice, clean 5. But the argument, that's where you have to be careful. Your calculator might give you a negative angle. But we know from our diagram the point is in the second quadrant, so the angle has to be obtuse. We have to adjust the calculator's answer to find the correct angle, which is about 2.21 radians.
Okay, ready for another one? Let's try a full conversion from start to finish. Our next number is w equals -7 plus 5i. We're going to find the modulus, find the argument, and then write it out in that final form. First up, the modulus, square root of -7 squared plus 5 squared, which gives us the square root of 74. Next, the argument, and once again, negative real part, positive imaginary part, that puts us squarely in the second quadrant. So we calculate the angle and adjust for that quadrant, which gives us about 2.52 radians. Finally, we just assemble all the pieces into our final modulus argument form.
All right, let's try a typical exam question. This is exactly the sort of problem you'd see on a test. We need to convert z equals -1 minus I.
Let's walk through it together. The modulus is the square root of -1 squared plus -1 squared, that's just the square root of 2. For the argument, a calculator might tell you the angle is pi over 4. But wait, both parts are negative, so our sketch shows we're actually in the third quadrant. This means we have to adjust that angle all the way around to 5 pi over 4. Then we just put it all together for the final answer.
Okay, one last challenge for you, and this one's got a little root in it to keep things interesting. How would you express z equals -2 plus 2 root 3i? Let's break this one down real quick. The modulus calculation works out to a nice clean 4. For the argument, we've got the inverse tan of -√3. We check our quadrant, negative real, positive imaginary. Yep, that's quadrant 2 again. So the correct angle is 2 pi over 3. Putting it all together, we get our final form. See? By now, you've got all the skills you need to solve these. So let's recap. We've gone from a simple line to a whole two-dimensional plane. And that lets us describe complex numbers not just by their coordinates, but by their distance and their direction. And that's really the big idea here. This modulus argument form isn't just a new way of writing things. It's a whole new way of thinking that unlocks some incredible power. Which leads me to one last question for you. What do you think happens to tricky operations like multiplication when you can just multiply the distances and add the angles? Well, that's a story for another time.